So we need to start looking at Greens Theorem. So we'll start by looking at a statement of Greens Theorem. Let R be a simply connected region with a piecewise smooth boundary C oriented counterclockwise. If M and N have continuous partial derivatives in an open region containing R, then we have the equivalence of these two integrals. On the left, we have a line integral, and on the right, we have a double integral, or an area integral. And so Greens Theorem allows us to move between the two forms. It may be that a line integral is easier to evaluate than the double integral, or vice versa. The double integral may be easier to evaluate than the line integral. So let's pull this theorem apart a little bit and focus on the assumptions or the hypotheses, and then the conclusion. So let's start with the statement that R is a simply connected region with piecewise smooth boundary C oriented counterclockwise. There's a lot of information in that statement, so let's kind of pull it apart a little bit. This first statement is actually the first assumption, that we have a region R that is simply connected with a piecewise smooth boundary C that is oriented counterclockwise. So let's go ahead and start by looking at the phrase simply connected region and see what that conveys to us. A simply connected region is basically a region that is bounded by a simple curve. So first of all, let's talk about a simple curve. A simple curve is a curve that does not cross over itself. So we could easily just say to ourselves, okay, what would a simple curve look like? What might a not simple curve look like? So a simple curve could look like this, because that curve does not cross over itself. A not simple curve would look maybe like that, because that curve does cross itself. A simple closed curve would look like this. Okay, and this curve is closed because there's no gap. Notice that this simple curve has a gap. This simple curve starts and closes at essentially a same point. A not simple curve could also maybe look like this. Okay, that's not simple because it loops over on itself. It is closed, however, because it does start and stop at a single point. So remember, we were trying to deal with this idea of simply connected region. So now that we have an understanding of what a simple curve is, then a simply connected region is a region that might look like these. I could have a shape like this, and this would be simply connected. It's bounded by a simple closed curve, and every point inside is bounded by that simple closed curve, and there are no points inside the closed curve that are not in the region. Now let's compare that to something like this. Something that maybe looks like a washer. Okay? This would not be a simply connected region. It is bounded by a simply closed curve, this outer circle, but it's not simply connected because there are points inside that simple closed curve that are not in the region. So we could say, kind of intuitively, that a simply connected region does not contain any holes like this one did. There is one other issue with respect to simply connected regions, and that would be this. If I had a region that, in essence, I could think of as being composed of two separate pieces, that would not be simply connected. Okay? So a simply connected region is a single region bounded in essence by a simple closed curve. It has no holes in it and is not in separate pieces. The piecewise smooth boundary part of this definition, okay, well, that's important because that tells us that here's our region. C is the boundary of that region, and it has to be smooth in pieces. So, for example, this would be a piecewise smooth boundary. Basically, there's no sharp points in the pieces. I could also have a piecewise smooth boundary. That's a rectangle. Because that's a triangle. Because the triangle consists of three pieces, and each of these three pieces are lines, and lines are smooth. So this could be our region on the outside, and the boundary would be the curve C. And piecewise smooth pieces. So there would be three pieces. Now the next important part is the fact that the boundary is oriented counterclockwise. That means we have to go around the boundary in a clockwise manner, or counterclockwise manner. So we have to go around the boundary in that direction. Okay, so that is the first assumption, but it carries with it a lot of information. Now, the second assumption with Greens' theorem is that the functions m and n have continuous partial derivatives in an open region containing R. Okay, so the second assumption, if m and n have continuous partial derivatives in an open region containing R, then we can apply Greens' theorem. So let's just take a look at this integral, and basically we just want to answer the question, does Greens' theorem apply to this integral? So we have the integral over curve C of x over y dx plus y over x dy, where C is the unit circle. So first let's look at the region R and the curve C. We know that R has to be a simply connected region bounded by a piecewise smooth curve. Well, the region is the interior of this unit circle, and the curve C is the unit circle, so certainly the unit circle is piecewise smooth, and the interior of that, the disk, is certainly simply connected. So this does satisfy the first assumption of Greens' theorem. The second assumption, though, is that m and n have continuous partial derivatives in that region. So let's just take a look at m. And if I take the partial of m with respect to x, that's 1 over y. And is the function 1 over y continuous in our region? And this is not continuous in the region R. And why not? Because y equaling 0 creates a problem, a discontinuity. So all along the x-axis here are points of discontinuity for this partial derivative. I don't have to check any of the remaining partial derivatives because I know immediately that it fails for this one, so I cannot apply Greens theorem.